So now we are going to move to a next section, section 1.3, real numbers and okay, real okay, what's happening? Real numbers and their decimal expansion. So we have seen that there are two types of real numbers. Okay, let me note down here. There are two types of real numbers. One are rational real numbers, okay, and the other one are irrational real numbers. So in fact, rational numbers and the collection of rational numbers and irrational numbers together, it's called as real numbers. So in this section, we want to see, or we want to rather observe, the decimal expansion of both these numbers, rational numbers and irrational numbers, and how the decimal expansion is unique when it comes to both rational numbers and irrational numbers. So let's scroll down and first focus on this set of rational numbers that we have here. Okay, so rational numbers and their decimal expansions. I have four rational numbers here, a, b, c and d, and there's one more here, e, and we are going to try to find the decimal expansion of these rational numbers and make some observations. Now first of all, we all should agree, we all should note that these are valid rational numbers. They are of the form p by q, where p is any integer and q is any integer other than 0. So these are all valid rational numbers. Now let's try to find their expansions. So first I'm going to go to 23 by 5. Okay, so we're going to divide 23 by 5. 23 divided by 5. So 5 fours are 20. Okay, 3 is the remainder. Then we give a decimal point, so it becomes 30. And then we have 5 6 are 30. So that is equal to 0. And thus we say 23 divided by 5 is equal to 4.6. Okay, let's continue with the next example, 27 by 4. Once again, we are going to perform the division. So let me write here 27 divided by 4. So 4 6 are 24, and then 3 is the remainder. Then I give my decimal point, so this becomes 30. Then 7 4s are 28, so 2 is the remainder. Then I add another 0, and then we have 4 5s are 20, and then my remainder is equal to 0, and my division stops. So 27 by 4 in decimal can be written as 6.75. Okay, so as you can observe that these two divisions or these two rational numbers can be expressed as 4.6 and 6.75. So their decimal expansion is terminating. It terminates. So this division terminates after a certain point because the remainder is 0, and we get a decimal expansion of these rational numbers. But this is not the case with all the rational numbers. In certain rational numbers, as we will see now, these 10 by 3 and 7 by 6, the division continues. The division never ends. So how does it happen? Let's have a look. Now we have this example 10 by 3. So let's continue with our process. Let's do the division. So 3 3s are 9. Okay, so 1 is the remainder. I put a decimal point, then I get a 0. Then once again 3 3s are 9. So minus 9, 10 minus 9 is 1 is the remainder. Once again I'll put a 0. And then we'll again get 3 3s are 9. So once again 10 minus 9 is 1, and we put a decimal. So that becomes 10. And once again it will be 3 3s are 9. So as you can see that this division continues. This division never stops, unlike the division that we saw previously where the remainder came 0 and then it terminated. Here you can see a repeating process. Every time the remainder is 1, and every time it becomes 10, and then we do 3 3s are 9. So if you note down this expansion, the decimal expansion of 10 by 3, you can see that the digits are repeated forever. So I'm going to mark this dot 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 dot. So continuously non-stop dot dot dot. This division will go on happening, and thus these digits will keep on repeating. So I can say very safely that 10 by 3 is now equal to 3.3333 repeated continuously and infinitely. And there is a way to represent this. It is written as 3.3 and a bar above it. So this bar indicates that this digit 3 is repeated infinitely to the right hand side. So 10 by 3 can be represented as 3.3 bar. So this is the decimal representation of this rational number. It is different than this decimal representation. Here there is no bar because the division is terminating and we have a finite numbers to the right hand side of the decimal point. Now similar to this 10 by 3, we have 7 by 6 where this division will be infinite. Let's see how it works out. So let me zoom in here. So we have 7 divided by 6. So I'm going to write 6 here, 7 here. Okay. So we have 6 ones are 6, minus 6, 1 is the remainder. So decimal 0, again 6 ones are 6, minus 6, 4 is the remainder. Then we come to 40. Then we have 6 6 are 36. And once again 4 is the remainder. And then we have 40. And then once again we have 6 6 are 36. Okay. So 40 minus 36, and again 4 is the remainder. And once again we have 40. And once again we have 6 6 are 36, so on and so forth. This goes on infinitely. So thus here we can see in this division, okay, in this division we have 1.1, but after this digit 1, 66666 keeps on repeating infinitely. So I can very safely write that 7 by 6 is in fact equal to 1.1666 infinitely. And if the digits are repeating, what we do is we put a bar around it. Okay. So 7 by 6 can now be represented as 1.16 bar, where the digit 6 keeps on repeating infinitely to the right hand side. Okay. So this representation is a little different than this representation. Here after decimal we just have one digit which keeps on repeating. Here after decimal we have one digit which does not repeat, and then we have the second digit which keeps on repeating. Similarly, very similarly, we have this another division 1 by 7, and I am not going to perform this whole division, but you can do it as a homework and confirm that 1 by 7 is equal to 0.142857, and then again 142857 and dot dot dot. So here you can see that this whole block, this 6 digit block keeps on repeating again and again. Here we had only single digit repeating. Here we have a block of 6 digits which keeps on repeating. So the way we represent this is 0.142857 and a bar around this whole. Okay, this indicates that this whole block of digits keeps on repeating to the right hand side again and again. Okay, so this is how we can represent 1 by 7. So now let's come back to our, so the point from where we started with rational numbers and then decimal expansions. We saw two rational numbers where the decimal expansion terminates, and then we saw three examples of rational numbers where the decimal expansion does not terminate, but it is recurring, it is repetitive. The word recurring means repetitive. So the digits keeps on repeating again and again to the right hand side, and thus I can write this. Okay, so this is something called as, I'm going to write here terminating, because the division terminates. Okay, and this example here was non-terminating. Okay, I don't have space. Cool. So this example here, it's non-terminating, so I'm going to write here non-terminating because the division does not terminate. However, it was non-terminating and recurring as in repetitive. It was repeating, the digits to the right hand side of the decimal were repeating. Okay, now so this is all about the rational numbers and their decimal expansion. Now if we come to irrational numbers, let's come to irrational numbers and their decimal expansion. So we all know by the definition of irrational numbers are numbers where the digits to the right hand side of the decimal go on infinitely. So it's 1 2 5 6 7 3 8 1 9 8 6 2 5 3 dot 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 dot. So this is an example of an irrational number. Now note the difference, that in irrational number the digits that repeat on the right hand side of the decimal, they are not repetitive. Okay, so to put it in the words, it's a non-terminating. Okay, the decimal expansion is also non-terminating and it is non-recurring. It is non-terminating and non-recurring, which means the digits do not repeat themselves in a certain pattern. Okay, in this example there was a pattern in which they used to repeat themselves, so we said it's a recurring decimal expansion. In this you can see there is no pattern, there are random digits which keep on occurring to the right hand side of the decimal point. So we say this is a non-recurring decimal expansion for irrational numbers. Okay, so thus now a very important conclusion. Okay, here we are. So we were checking real numbers and their decimal expansion. Okay, so now the decimal expansion of real numbers have two possibilities. Let me zoom in more. Yes. So the decimal expansion of real numbers have two possibilities. Either the decimal expansion will be terminating or it will be non-terminating. And if it is non-terminating, it will be either recurring or it will be either non-recurring. Okay, and very importantly, if it's terminating, okay, then it is a rational number. Okay, so if we have a real number whose decimal expansion is terminating, it's a rational number. Now next, if we have a real number whose decimal expansion is non-terminating but recurring, so that is also a rational number. That is also a rational number. However, if it is non-recurring, it's non-terminating as well as non-recurring, then that is an irrational number. That is an irrational number. So we thus observe that the decimal expansion of real numbers uh, can be a rational number or irrational number. For each of these numbers, rational numbers or irrational number, their decimal expansion have different properties. If you take any irrational number, its decimal expansion is going to be non-recurring and non-terminating. And if you take any rational number, its decimal expansion will be either terminating or it will be non-terminating and recurring. So this is how we observe that the decimal expansion of a real number can be used to classify whether a number is a rational number or a irrational number.